So as I said yesterday, this video is going to be really short, probably 20-ish minutes at best. And we'll look at properties of integrals. Later in the day, I will put up a review sheet which will include all the concepts that we have covered from the first day, and I'll probably try to highlight the things that I feel are more important, and I will be giving higher weightage to that during the exam. So don't take it as the 100% certainty that this is what a question will be on and this is not what a question will be on. But when I'm designing an exam, these are the concepts that I feel are more important, and there's a higher likelihood of me trying to involve these concepts is what the point will be. Okay? So properties of integrals. Theorem 6.12, part A. Suppose f1 and f2, f1 comma f2 belong to R alpha on AB. Okay, so if f1 comma f2 belong to R alpha, then f1 plus f2 also belongs to R alpha of AB. On AB, and so does C times F belonging to alpha, C times F1 belonging to C. Well, maybe I should remove so does, because there are multiple things that I want to say. C times F belongs to R alpha for every constant alpha, for every constant C, every constant C, and we have the nice properties that integral from A to B f1 plus f2 d alpha is equal to integral from A to B of f1 d alpha plus integral from A to B of f2 d alpha, and integral from A to B of C times F alpha, C times F d alpha, well, I will say f1 d alpha is equal to C times integral from A to B of f1 d alpha. Okay, so you can pull out the C from the integral. B. All of these are properties you have seen before for Riemann integrals, probably in Calc 3, right? When you first get introduced to integration, maybe Calc 2, I don't know, depending on the course you took. But here we are showing these results for a slightly generalized function. We are not showing this for just Riemann integrals. These are style-just integrals, right? Riemann style-just integrals. If f1 of x is smaller than or equal to f2 of x on a comma b, then integral from a to b of f1 d alpha is smaller than or equal to integral from a to b of f2 d alpha. Okay, and part C. If f belongs to R alpha, d alpha, R alpha on AB, and if A is smaller than C is smaller than B, then f belongs to R alpha on AC, and on CB, then f belongs to R alpha on entire AB. We already assumed that it entire belongs to R alpha on the entire AB. So the integral from A to C f d alpha plus integral from CB C to B f d alpha is equal to integral from A to B of f d alpha. Okay? For D. If f belongs to R alpha, R alpha on AB, and if absolute value of f is smaller than f on AB, then absolute value of the integral A to B f d alpha is smaller than or equal to capital M. Well, yeah, that's like alpha of B minus alpha of A okay, and part E finally, if f belongs to R alpha 1 and f belongs to R, not R, R of alpha 1 and R of alpha 2, then this is something nice. F belongs to R of alpha 1 plus alpha 2. Okay? And integral from A to B f of d alpha 1 plus alpha 2. Oops, put the brackets in the wrong place. F d alpha 1 plus alpha 2 is equal to integral from A to B of f d alpha 1 d alpha 1 plus integral A to B of f d alpha 2. In particular, this also means that if f belongs to R alpha and C is a constant, C is a positive constant, it is important that C is positive because otherwise R would not be a monotonic increasing function. If you take a negative constant, it is decreasing, and R alpha is only allowed to be monotonic increasing. Then f belongs to R of C alpha, and integral from A to B of f d C alpha is equal to C times integral A to B of f d alpha. Okay, I am not going to prove all of these. In fact, the reason I'm not going to prove all of these is because a proof of some of them is really simple, okay? And I'm going to leave them as exercises because they're so easy, technically, I could give them on exam, okay? So these are potential questions for the exam, since the proofs are really simple for some of these, okay? How do we prove this? If f is equal to f1 plus f2, well, this is A, right? What does A say? Well, in that case, it belongs to f1. F1 plus f2 is integrable. Well, if it's Stahlhaus integrable for f1 is Stahlhaus integrable and f2 is Stahlhaus integrable, then here's something that is going to happen. If P is any partition of AB, and if P is any partition of AB, then we have L of P F F1 alpha plus LFP-F2 alpha is smaller than or equal to LPF alpha is smaller than or equal to U of PF alpha, PF alpha, okay, is smaller than or equal to U of PF1 alpha plus U of PF2 of alpha. Okay? Why is this true? Look back at how L and U are defined. If both the minimums are at the same place, then these are equal. If the minimums are at different places in the interval, in the partition, then these might be different, right? In which case, if f1 comma f2 belong to or alpha and epsilon greater than 0 is given, I can find partitions P1 and P2. We can find partitions. There are partitions. There are partitions P1 comma P2 such that U of P I Fi alpha minus L of Pi Fi alpha is smaller than epsilon. What do you do then? Take their common refinement. Taking their common refinement P, common refinement P, we get from the from this, from star, that U of P comma F comma alpha minus L of P comma F comma alpha is strictly smaller than 2 epsilon. I can't say epsilon because I'm taking UPI plus FPI, like both of them are getting added, but this is smaller than 2 alpha, and therefore F belongs to our alpha. Okay. If I do this with the same P, I can show that there we go. Okay. With the same P, we have for the same P, for this same P, we have U of P F1 alpha smaller than integral Fi comma alpha Fi d alpha plus epsilon, right? Because it's a refinement of Pi, so this is true. Therefore, I have that, well, if this is smaller, I am going to have that F d alpha on A to B is smaller than UP alpha PF1, F comma alpha, which is smaller than, well, this is true because it is in our alpha, right? FD alpha is in our alpha, so this is integral FD alpha is smaller than UPF alpha, and integral F1 d alpha plus integral F2 d alpha plus 2 epsilon, right? Well, since it is arbitrary, I can make this smaller, and therefore, as epsilon is arbitrary, or BIT, B, I, T, or A, or Y, we conclude CL and conclude that integral from a to b of f d alpha is equal to integral from a to b of f1 d alpha plus integral from a to b of f2 d alpha. Okay? Well, technically, this gives you smaller than or equal to. Do the same for L, and you can show that it's greater than or equal to, and hence that you have equality. Okay? How do you show for C? For constant C, prove it for every refinement. U of P comma F CF comma alpha is equal to L is equal to C times L of P comma F comma P comma F comma alpha. Okay, so you don't even need to go that far. You can just pull it out here. Similarly for L, comma U of P comma CF comma alpha is equal to C times L of P comma F comma alpha. Not L, U. Right? So that is that. Most of these proofs are similar. Part E is going to be very slightly more complicated, but it's not as much more complicated because what is the condition that it's going to be? You split it onto intervals. On each interval, you have this, right? Sorry. What did I want to say? Okay, for part C, for part C, take a refinement of take refinement P, take refinement P, which includes C as a point, which contains C as a point. Okay. As I said before, I'm not going to be proving all of these. I will leave a lot of them for you. How long is it? It's been 18 minutes. Okay, let me do one more result. Term 6.13. This is if f belongs to R alpha, and if f comma g belong to R alpha, and on AB, then the following are true. First, A, f times g belongs to R alpha. Okay? And second, if absolute value of f belongs to R alpha, and not if, absolute value of f belongs to R alpha, and integral from a to b f d alpha is smaller than or equal to integral from a to b absolute value of f d alpha. Both of these are relatively easy to prove. Okay. I'm not going to give full detailed proof. I'm not going to ask you these on the exam. Okay. These are slightly complicated. Well, yeah, not slightly complicated, but I'm showing you the entire proof anyway. If we take phi of t is equal to t squared, then theorem 6.11 shows that f squared belongs to alpha. F squared belongs to R alpha. R alpha if f belongs to R alpha. Okay. Now here's a really, really nice trick that you do. Okay. Then the identity that 4fg is equal to f plus g squared minus f minus g squared completes the proof of A. Completes proof of A. Each of these is integrable by what do you call it? The previous theorem, right? And so 4fg is also integrable, so fg is integrable, right? Now, if we take phi of t is equal to absolute value of t, theorem 6.11 again shows that absolute value of f belongs to R alpha. R alpha. Okay. In that case, choose c is equal to plus minus 1, so that c integral f d alpha is greater than or equal to 0, right? Then what is absolute value of integral f d alpha? Well, you can actually break it down into things, or this is c times integral f d alpha. Okay, so break it down. There are multiple ways of showing this. Okay, but I guess this is more direct. C d alpha is equal to c times f d alpha. Since the absolute value of negative number is positive, blah 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 blah, and this is smaller than or equal to integral absolute value of f d alpha, since cf is smaller than or equal to absolute value of f, right? And that completes proof of B. Okay, so as promised, this is a really short lecture, and wanted to stop. I wanted to cover these properties because these properties are A, really important to know, B, they're really easy to prove. So they are something you should know, and they could be used as questions. Okay, so go through them, try to prove them on your own. Okay, most of them are really easy. If I do give one of them, it will be easier, or it will be a very slight modification of one of these properties, and it'll be very easy to show with these. Okay? I will try to upload a review sheet by the evening. I will also have extra office hours tomorrow instead of having office hours on Thursday. I will let you know the timing soon. Okay?